Chapter 5 is on quadratic functions, and the first thing we'll be doing is looking at properties of quadratic functions. Guess we better start by saying what a quadratic function is. A quadratic function can be written in the form y equals ax squared plus bx plus c, but it's only valid if a, b, and c are real numbers. Basically all the numbers we deal with in high school, so no big deal there. And a cannot equal 0. Why can a not equal 0? Because if a equals 0, you would have no x squareds. So you'd actually end up with something like y equals bx plus c. And if you have that, you actually have not a quadratic function, you have a linear function, right? That's like all the things we've already done, graphing in grade 8, 9, 10. You'd had things like y equals 2x plus 3, or y equals negative 1/2 x minus 4. Right? In this case, these are linear. What makes a quadratic is that x squared part. So you can't have a 0 there, you'd have no x squareds. Alright, so that's what makes something quadratic. I'm going to quickly mention a few things that look like they're quadratic functions, but they actually aren't. I think we did this when we talked about polynomials, but I'll do it again. So not any of the following. These are not quadratic. Not quadratic, alright. Okay, one thing that's not quadratic is if you have something like y equals 2x squared plus 3 times root x plus 6. Okay, if there was no square root sign, it'd be great, but that is no good because of the square root sign. You can't have a variable, an x, inside a radical sign. It's not quadratic in that case. Okay, another one is y equals 2x squared plus 3x. That looks good so far, but I'm going to put to the 1/2. And that should make sense because remember, anything to the 1/2, it's the same thing as the square root of. If you remember from the first chapter we did this year, x to the 1/2 is the same as the square root of x. So these two things are actually exactly the same. Another thing that won't work is if you have this y equals 2x squared plus 3x to the negative whatever, negative 2 I'll put. That's no good. Can't have a negative exponent on the variable. And the final thing is much related to that. What does the negative exponent mean? Remember, it's a flipping negative. That would flip the x down here. So these second two things are also more or less identical to each other. So just to summarize, it's not quadratic if your variable is in a radical sign, if your variable has a fractional exponent, if your variable has a negative exponent, or if your variable is in a denominator. This is a very minor piece of the chapter, but I just thought I'd throw it out there. And I believe we did talk about that before when we talked about polynomials, because it's the same. I could also say not polynomials and write all this as well. Alright, let's move on. So I already said this, well no I didn't say that. They're second degree polynomials. Quadratic functions are second degree polynomials. Now I don't want to really get into degrees again, but basically degrees is looking at the exponents on the variables. So the highest exponent we have in here is a 2, and that's why it's a second degree polynomial. And that's what makes something quadratic. That's why, as I said, you can't have 0 here. Otherwise you have no x squareds. The highest exponent you'd have on a variable is a 1, so it wouldn't be quadratic. It would be linear because it would have a degree of 1. But this one has a degree of 2. And all the graphs will be parabolas for quadratic functions. A parabola is like this shape, this blue shape right here. That is a parabola. Okay, so what this section is all about is looking at the properties of this, or not particularly this parabola, but of parabolas. What are some of the features that we can identify of a parabola? Okay, well one thing is the y-intercept. So we've talked about y-intercepts before. What's a y-intercept? A y-intercept is where the parabola crosses the x-axis. So in this drawing here, the y-axis is right there. That's where it crosses the y-axis. So if we were going to name that point, if we were going to say what the y-intercept is in this case, you could just say -3, or you could actually name that point 0, -3. It's probably a little safer to write this, or if it's really clear you're talking about the y-intercept, you could just say -3. Okay, how would you find the y-intercept if you just had the equation? Well, what you do is you set x equals 0. Remember, every point on this y-axis here has an x value of 0. This point here is 0, 3. This is 0, 2. This is 0, 1. This is 0, negative 3. This is 0, negative 5. They all have an x value of 0. So if you set x to 0 in the equation, plug 0 into all the x's, you'll find out what the y value is at that point, and that'll be your y-intercept. Okay, how many y-intercepts can there be? Well, there will always be exactly one y-intercept. Now some people say, I don't agree with that, Mr. Wodge. I think if I had a parabola that looked like this, I would have no y-intercept. It doesn't look like it is going to have a y-intercept, but remember, this is getting wider and wider and wider and wider here. Eventually, somewhere way up high, that's going to cross over the y-axis. Okay, so that's always the case where there's a one y-intercept. Oh, wait a minute. Some of you might have said, well, wait a minute, Mr. Wodge, what about something like this? And that's good thinking. That would have no y-intercept. However, for grade 11, we will not be dealing with parabolas facing out to the left or facing to the right. All our parabolas will either face downwards, like this one, or will face up. Okay, so everything I say here about the properties of parabolas, it's based on the fact that we're only dealing with parabolas facing down or up, no sideways parabolas. Alright, next thing, x-intercept. Well, that's pretty clear. If we know what the y-intercepts are, we should know where the x-intercepts are too. They are the points where it crosses the x-axis. So we have one here, and we have another one right there. If I was going to name those, I would say that this one is 1, or I could be more specific and say 1, 0, and this one is 3, or I could be more specific and say 3, 0. So these are the points where the parabola crosses the x-axis. Guess how those can be found? Well, all the points along the x-axis all have a y value of 0. This is 1, 0, 2, 0, 3, 0, negative 2, 0. So this time you set y equals to 0 and solve. It'll be a little bit more difficult, and we'll show you an example of that later. How many can there be? There's 2 in this case. Can you think of some other possibilities? Well, you could have none. How could you have none? What if it looks something like this? Right? That's never going to cross the x-axis. Same if you went like this. Never going to cross the x-axis. Any other possibilities? You could have none. You could have 2. You could also have 1. What if the lowest point was right there and it went like that? Or what if the highest point was right there and it went like that? So you can have 0, 1, or 2 x-intercepts. So let's write that down. Next is the vertex. This is the most important point to the parabola. This is that point I was just talking about, the highest point or the lowest point. So this is our vertex right there. So how it's defined, it's the highest point or the lowest point of the parabola. In the parabola we're looking at right here, the parabola is, or the vertex is 2, 1. You must say 2, 1, of course. There's no other way to name that point. So 2, 1 is what you would call it. There's different names for the highest point and lowest point. If it's the highest point, like this one, that is called the maximum. And that makes sense, right? That's the highest point or the maximum point of this parabola. If you had a parabola facing upwards like this, or opening upwards we say, then the vertex is down there, and that is called a minimum. There's no point lower than that point, so it's the minimum value or minimum point. Next, axis of symmetry. So for the axis of symmetry, what does symmetry mean first of all? Kind of makes you think of mirrors or something, right? It's when one half of something looks exactly the same as the other half. So there is a axis of symmetry here. I will draw it in with a dotted line. There we go, I've put it in red. And you can see that line is like a mirror line where the left-hand side of the parabola totally matches up with the right-hand side of the parabola. It's like they're reflections of each other. And this is the axis of symmetry. You'll notice that the axis of symmetry goes right through the vertex. And that'll always be the case. So it's the imaginary vertical line that passes through the vertex. Notice it's imaginary. It's not really there, right? I just drew it in now, but it wasn't really there. It's just an imaginary line. And the equation is always going to be x equals m. Huh? What am I talking about? Well, if I wanted to name this line, this dotted line right here, how would I name that? Think of all those points. This is the point 2, 0, 2, 1, 2, 2, 2, negative 2, 2, negative 3. Oh, it's all the points that have an x value that's equal to 2. So basically the equation is always going to be x equals m, where m is the x coordinate of the vertex. So for example, if you had a parabola that went through the point 7, negative 3, then the axis of symmetry would be at x equals 7. Even without drawing it, I know that that's a fact. Okay, that'll always be the case. Okay, next is domain. Remember domain? Domain is all the x values that are associated with the parabola. So if you think of this parabola and look at the x values. Remember, this is getting wider and wider and wider and wider, so it's going to eventually go, well, not eventually, it is going forever to the left. And if you look here, it's getting wider and wider and wider. It's going forever to the right. So the domain is going to be from negative infinity all the way up to infinity. Remember doing this last year? And that's always going to be the same. Remember that I'm only dealing with parabolas that are facing down like this or facing up. And because we're only dealing with those ones, the domain will always be all real numbers. So domain's the x values of the parabola, and it's always going to be, you can write it in two ways. You could say x is an element of all real numbers. Remember we wrote it like that before. Or you could write the other method, which is from negative infinity all the way up to infinity. It's the same thing. You can see two ways you can write that. Okay, range. If domain is x, you might remember that range is the y values. So if we look at the y values of this, it goes down and down and down and down. Down forever. It goes all the way down to negative infinity. It goes up and up and up. Whoop, that's the highest point. Remember, it's a maximum. So the highest point is 1. So the one we have here, this parabola we have here, it goes from negative infinity up to 1, including 1, so I put a square bracket. Or the other way you could say that is all the y values are less than and equal to 1. And in fact, it's very similar. It's always going to be like this if you have a maximum like we have. We have a maximum. If it opens up, well, let's start with this one. If it opens down, like this one we have right here, the parabola is opening downward. And if that's the case, your equation is always going to be y is less than or equal to n. What's n? N is the y coordinate of the vertex, right? If you look at my range right here, y is less than or equal to 1. And 1 was the y value of the vertex, so that worked out perfectly. The other way you could write this is it will always be from negative infinity up to n. That's the other way you could write it if it opens down. Now if it opens up, again, n is going to be the y coordinate, of course. It's not going to be y is less than or equal to n. It's going to be y is greater than or equal to n. In other words, it's going to start at n and it's going to go up to infinity, like that. And that'll always be the range. If it's opening up, it'll be in that form. Okay, you'll get used to this. I know it sounds pretty complicated, all the stuff I've done here, but you're going to get used to it. In fact, we'll do an example right now, and I bet you'll surprise yourself how much of this you understand. Okay, this parabola right here, let's find the vertex. Well, that's not bad at all. Here's the vertex right there. What's that point? Negative 1, 4. I'm finished. Hey, that was pretty easy. The axis of symmetry. So again, I'll draw the axis of symmetry. You don't have to, but I'll draw the axis of symmetry in case you don't know what I'm talking about here. There we go. What's the equation of the axis of symmetry? Now, oftentimes people just put negative 1. That's not an equation. Remember what we said? We said that the axis of symmetry will always be x equals m, where m is the x coordinate of the vertex. So in this case, it should be x equals negative 1. And if you look at that axis, yep, that goes through negative 1. All those points have negative 1 as their x value. That's definitely the axis of symmetry. Y-intercept. Y-intercept's right there. You could just say 3, but I prefer 0, 3. X-intercept, or intercepts in this case, I have one here. That's at negative 3, or I'll say negative 3, 0. It's more specific. And I also have one at 1, 0 as well. That's an S for x-intercepts. Domain. Don't even need to think about this question when you have it in Pre-Calculus 11. Domain will always be x is an element of all real numbers, or if you want, from negative infinity up to infinity. That's horrible, but that's negative infinity there. The range, you do have to think about a little bit. We have a maximum here, so in other words, all the y values are less than or equal to that maximum, and the maximum's at 4. The other way you could write that, it goes down forever, down, 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 so to negative infinity, but it only goes up as high as 4, inclusive. And is this a minimum or maximum? Well, that's the highest point. This vertex is the highest point, so it's a maximum. And what we say is it's a maximum of 4 when x equals negative 1. Sometimes it's written like that. Or you might just be telling me it's a maximum. That's fine too. Alright, now this is kind of weird, but I have the exact same things written down again, and what I'm going to show you is you can actually figure these things out if you didn't even have the graph, if you just had this equation. So this is the equation, y equals negative x squared minus 2x plus 3. This equation right here, if you were to graph it, you get that blue parabola right there. And I want to show you that if you just had the highlighted bit, you didn't even see the parabola, you could still get all this information. Now, I'm going to be showing you some stuff that we're going to learn later on in this chapter, but I still think it's worthwhile. So let me write it right here. Y equals negative x squared minus 2x plus 3. And here we go. We're going to fill it all in again. But we can't do it in the same order. Can't get the vertex yet. Later on we'll learn how to get the vertex really quickly, but we can't do that yet. And we can't get the axis of symmetry. But we can get the y-intercept. So let's do that first, the y-intercept. Remember how we said you could get the y-intercept? Plug 0 into the x's. So in other words, you're going to have y equals negative 0 squared minus 2 times 0 plus 3. Okay, 0 squared is 0, and then negative 0 is still 0, minus 0 plus, so just 3. Our y-intercept is at 3. Or if I want to write it as a point, it's at 0, 3. And if we look up here, yep, that's what we got, 0, 3. So that's good. X-intercept, how do we get that? To get the x-intercept, we put 0 into the y. So 0 equals negative x squared minus 2x plus 3. And now we have to solve this. So how do you solve this? This is a quadratic, and we did learn this actually before this year. If you have a quadratic, you want to make it equal to 0. You want to make sure your leading coefficient, this negative x squared, you want it to actually be positive, and then we're going to factor. How could we make this positive? Let's move everything over to the other side, because remember, we want it to be equal to 0, so we've got to move everything over. This moves over and becomes x squared, this moves over and becomes plus 2x, this moves over and becomes negative 3, and what's left on the right-hand side now is 0. And now we factor. This is simple trinomial. We're looking for two numbers that multiply to 3 and subtract to 2. So we've got x, and our numbers are 3 and 1. Drag down that plus, a positive times a negative equals that negative 3, and it's still equal to 0. Alright, where am I going to write this? I guess I'll keep going down here. If x plus 3 times x minus 1 equals 0, then either x plus 3 equals 0, or x minus 1 equals 0. I don't know why I'm putting in brackets. What would make this equal 0? If x equals negative 3. What would make this equal 0? If x equals positive 1. So here's our two x-intercepts. One of them is at negative 3, so it's negative 3, 0. And the other one's at 1, so it's 1, 0. And if you look up here, that's what we have, negative 3, 0, and 1, 0. Okay, the domain. Yay, we don't even need to think. It's always equal to all real numbers, so no problem there. Okay, I think the next thing we can do is we can find the axis of symmetry. I want you to picture this. You have two x-intercepts. One of them is at negative 3, 0, so right there, and one's at 1, 0, so right there. Can you tell me where the axis of symmetry would be? Remember, the parabola has to be like a mirror image of each other. So if you have an x-intercept here and an x-intercept there, the mirror would have to be right in the middle. In other words, the axis of symmetry has to be right in the middle of that. The axis of symmetry would be right here. Hope that makes sense. If not, don't worry about it too much. We're going to talk about this more later. But it has to be between negative 3, this point here is at negative 3, 0, and 1. And halfway between negative 3 and 1, if you take the average of negative 3 and 1, you get negative 1. So that means our axis of symmetry is at x equals negative 1. How does that help us for the vertex? Well, remember what we said before, the vertex is on the axis of symmetry. So somewhere on here has to be our vertex. How are we going to figure out where it is? Plug negative 1 into the x's, since we know that's the x value of the vertex, and whatever you get for y, that's the y value of the vertex. This is great. So y equals negative. Then I can put negative 1 into that first x, square it, minus 2 times negative 1 plus 3. Okay, what's that equal? Y equals. First of all, it doesn't mean negative makes a positive. That's wrong. First of all, you do negative 1 squared, which is positive 1, then slap that negative on. So it's a negative on. So it's negative 1. Negative 2 times negative 1 is plus 2, and plus another 3. Negative 1 plus 2 is 1, plus another 3 is 4. So I get the y value should be at 4, which means my actual vertex would be at negative 1, comma 4. Sure hope that's what it was up here. Let's see. Yep, negative 1, 4. Okay, we're almost done. The range. For the range I have to teach you something, and what it is pretty simple. If the leading coefficient, that negative, this x squared here, if it has a negative sign out front, it's going to face down. The parabola will face downwards. If it's not negative, it'll face upwards. So we have a negative sign, meaning it faces downwards, right? We saw that up there. But even if we didn't see the graph, if we only were given the equation, we would know it faces down because of the negative. So think about it. If it faces downwards, do we have a maximum or a minimum? We have a maximum. We have a highest point. So what's the range then? Well, if we have a maximum, then it goes down forever. It goes down to negative infinity. But how high does it go? It only goes as high as the y value of the vertex. It only goes up to there. If you wanted to write it the other way, all the y's are less than or equal to 4. There you go. Now, we actually did a whole bunch of stuff that we're going to learn later in the chapter, but I just want you to see that, these properties, you can get them from the graph very, very easily, but you can also get them just from an equation with just a little bit more work.